Hello everyone, welcome back to the tutorials of DAA Lab. I am Deepak Niyal and in this tutorial I am going to discuss about week 6 problems that are based on graphs. So particularly here we are going to talk about directed graph, undirected graph, weighted or unweighted graphs. If you want to know the basics, I will provide the link of two tutorials in the description. You can check the description and then come back to these problems. I hope those videos will help you to understand the problems and then you will be able to solve these problems clearly. I will describe some of the concepts here in this video as well. So let's start. Here we are going to follow a input format and this input format you are going to see in this week's problem and in coming week's problem. So consider example of below given graph which is given in figure A. So you can see here this is figure A. A Boolean matrix adjacency M, this is adjacency M of size V by B or V cross B is defined to represent edges of the graph. So here we have 5 nodes and when we are saying 5 nodes, it basically means V equal to 5. So this matrix is 5 cross 5. Here we have 5 and here we have 5 nodes. So V equal to 5. So this is defined to represent edges of the graph. Each edge of the graph is represented by two vertices, start vertex and end vertex. So here we have A and here we have A and it's 0 here. That means there is no edge between A and A. But in case of A and B, we have 1. That means there is a vertex from A to B. And then we have B and A here and it is representing 1. It means there is a edge between B and A also. It's a undirected graph. So if A and B has a edge, B and A should also have a edge. Clear? So you can see here that means an edge from U to B is represented by making adjacent matrix UV and adjacent matrix VU equal to 1. So you can see here if there is no edge between U and B, then it is represented by making this particular index equal to 0. So you can see there are many zeros here and at every place we have 0. That means there is no edge. Okay, so A and D has 0 here. It means there is no edge between A and D. Clear? Now, adjacency matrix representation of below given graph is shown in figure B. So it's clear this particular graph has a representation in adjacency matrix form like this. We basically could have two representation. One is adjacency list and another is adjacency matrix. So you can check the description for the explanation of adjacency list and matrix in detail. But here we are using this format and it is adjacency matrix. Clear? So here you can see hence edges are taken in the form of adjacency matrix from input. In case of weighted graph, an edge from U to V having weight W is represented by making this particular index and this particular index equal to W. It means if graph is weighted, that means suppose if A and B is 5 or maybe 10 or any other value, then what we are going to do here in AB, we will not have 1, we will have 5. And similarly, B and A will have 5 here. But this graph is unweighted graph, so we don't need to write these numbers. Just 1 and 0 is fine. Now, how to take input? For the input format, here we have 5. This is the first number. And what does this mean? It means that we have 5 vertices. That means we'll have 5 cross 5 matrix, right? And how to pass this to the program? You can just write this adjacency matrix in this format, right? You don't need to write ABC. Just write these numbers and separate them by space or comma, whatever you like, right? So you can see here input format for this graph is shown in figure C. First input line will obtain number of vertices. Here is this. After first line, V input lines are obtained. So these are V input lines. In this case, V equal to 5. For each line I in V, it contains V space separate Boolean integers representing whether an edge is present between I and all other vertices. So I hope you are clear with the problem statement now, right? If you want to learn these, just watch the videos that I have provided in the description. Now moving forward, given a directed or undirected graph, design an algorithm and implement it using a program to find if path exists between two given vertices or not. So here hint is given that you should use DFS, but there are other ways also. Let me first explain the problem. Input will be graph in the form of adjacency matrix or adjacency list. So right now we are using adjacency matrix for this problem, but you can try adjacency list also. Okay. Now source vertex number and destination vertex number is also provided as an input. And what should be the output? If there is a path between these two vertices or not. Clear? So this is same input that we have taken above, right? And here is the graph. And source and destination vertices are 1 and 5. And it is saying that yes, path exists. Clear? And how do you know that path exists? Just go to 1, 2, 3, 4 and 5. So see if 1 and 5 has any path. No, there is no direct path, but 1 to 2 has a path and 2 to 5 has a path. And that means 1 to 5 has a path, right? Now let me tell you a few more things before approaching this problem. So what you have to do, you have to just see whether graph is directed or undirected. So these are two things, right? Other than this, you have to check whether graph is weighted or unweighted, right? So once you are done with these things, to find out whether there is a path between two vertices or not, you can use a simple algorithm, that is Floyd-Warshall algorithm, right? So what it does, it's a algorithm to find out the path or distance between one vertex to another vertex. Basically, it's a algorithm to find out the path between all pairs. Suppose we have 5 nodes, then it will find out path from 1 to all other vertices, and similarly from this to all other vertices, right? So that's how this algorithm works. We are not going to discuss this particular algorithm here in detail, but what you can check if there is a direct edge between these two vertices, and second, you can check if there is no direct edge, if a path exists between these two vertices or not, right? And you can take one as I and another j. So that's how you can use this algorithm. But we are not going to use this algorithm, and there is a reason behind that. And what is the reason? The time complexity of this particular algorithm is very high. It's V cube. And if you talk about space complexity, it's OV square, right? It takes a whole matrix. So we are not going to use this algorithm here. What we are going to do? We are going to use either BFS or DFS, right? So what is a BFS and what is a DFS? So these are two algorithms, and what is the full form of these algorithms? Breadth first search, and it is depth first search. So there is some meaning attached to these things, breadth and depth. So suppose we have a graph. Let me take the graph first. 0, 1, second vertex, third vertex, fourth vertex, and there's a fifth vertex, right? So basically you can use this BFS and DFS to find out the path between one vertex to another vertex. Suppose this is source vertex and third is destination vertex. So this particular algorithm use queue, and this algorithm use stack for this purpose. I will tell you algorithm in a while, but just understand the process first. So what we do in Q, so what we do in BFS, we basically start with source. So just put this thing in Q, and once we have 0 here, or let me start it at the end. So this is Q. We have 0 here. So once you have got 0 or this particular vertex, just find out all its neighbors. And there are two neighbors. So it will pop this out, or we can say we will dequeue this particular node. Let me remove it from here and then put 1 and 2 here, right? So what it is basically doing, it is exploring all the vertices that are attached to this particular vertex. So that's how BFS is functioning, right? But what happens in DFS, we basically have a stack, and how it functions, what we are going to do, we are basically going to take the first one, that is 0th vertex, and we call it source vertex. And when we have visited this particular vertex, just pop this out. Let me remove it. And once you pop this out, find out another vertex that is attached to this, either 1 or 2. We can take any one of them. Suppose I am taking 1, so only 1 will come here, not 2, as in case of this, right? And once we pop this out, we'll move to another vertex, that is second, and that's how it goes, right? But what happens in BFS case? Now we are going to pop this out, or we are going to dequeue this first. Now see which are neighbors of 1, 3 and 4. 0 is also neighbor, but it's already visited, so we are not going to take that. So 3 and 4 are there, so we'll keep 3 and 4 in the queue. And that's how this particular algorithm uses queue, and this particular algorithm uses stack, right? I hope you have got an idea about it. Now I will tell you the algorithms of BFS and DFS, and the way these algorithms are going to find out path between two particular vertices. Let me show you the BFS algorithm first. I am writing a function here, is path BFS, and what I am going to take a graph, source vertex and destination vertex. So first you have to do, take a queue, and you can name this queue as Q, okay? And in this queue you have to enqueue source vertex first, right? And once you do this, mark S as visited. So we'll mark this particular source node as visited. And how do we do that? We take an array. Suppose we have 5 vertices, 1, 2, 3, 4 and 5, and we basically make them 0 at the first. But suppose one vertex, let's suppose 0 is visited. So what we are going to do, we'll mark it 1, right? So if 2 is visited, make it 1, and so on. That's how it goes on, right? Now moving ahead, write a loop here while queue is not empty. So if queue is not empty, keep doing some work, and what we are going to do, dequeue the queue. That means you need to remove some elements from the queue, right? And when you have removed an element, check all the neighbors of that particular element. So write for all neighbors u of v. So for the all neighbors of v, which you can see here is represented by u. So for all neighbors u of v, check this condition. If u equal to d, it means this particular node that we are going to check at this place is equal to destination, we need to return true. It means we have found a path. That's why this particular node that we are getting is equal to destination, right? One more thing we have to check, if u is not visited, we need to enqueue it because this particular node is not visited till now, right? And once you have enqueued this, we need to mark it visited, right? So we are done basically. But if none of these things happen, so at the end you can return false. It means path is not found. Okay, so you can run this particular algorithm for this graph and see if you are able to find out path between 0 and 3. Okay, next let's understand DFS, and for that I am writing another algorithm is path DFS. It means we are going to check whether there is a path between two vertices using DFS. So here we have graph, source vertex, destination vertex. Here we have to take a stack. So I will take a stack with name st, and then I will use this stack to push source vertex inside this. And once you are done, mark s as visited. So this particular node is visited now, right? And what we have to do, we have to again take an array of the same size as we have vertices. Suppose we have 5 vertices, so take this size as 5 and first make them 0. But when this particular node is pushed to stack, we can mark it visited. So here in this case, if this is the source vertex, make it 1, right? So that's how this algorithm works. Now what we have to do, we have to apply a loop here as well, and we have to check till stack is not empty. Okay, when stack is not empty, what we can do, we can start popping vertices from stack. So we'll use v equal to st.top. What this function does, it is used to reference the top element of the stack. Okay, so what we are going to do, we'll pop this particular element, and then what we are going to do, we are going to apply a loop here, for loop for all neighbors u of v. Okay, so we are going to check all the neighbors of that particular node and then apply a condition. If this node is equal to destination, we need to return true. It means we have actually found the path between two nodes, right? I hope it's clear to you. Now moving ahead, if this particular node u is not visited, we need to push this node to the stack. And once you have pushed it to the stack, just mark it visited. Okay, you need to use the array we have discussed above. And if nothing happens inside this loop and this stack is empty now, you can basically return false. It means there is no path. And when is that possibility when there is no path between two nodes? So let me tell you another graph where this possibility could occur. So above graph that we have discussed, you can consider that as graph 1. There is graph 2 also. Okay, you can draw as many as graphs possible. So here is we have 0th node, first node, second node, and this is third node. And in this case, suppose source is this and destination is 3, then there is no path, right? There is no path between 0 and 3. Whether you apply BFS or DFS, you will not find any path, right? So I hope you are clear with these algorithms. If you want to dry run these particular algorithms on the graph that I have discussed, you can do so, right? And tell me in comments if you have any issues with these things. Okay. There are two more questions that I am going to discuss in next two videos. You can just look at these first and tell me in case of any confusion or any problem. Okay, so see you in the next video. Till then, thank you so much.